All right. So now I just want to play one tutorial. I asked my student to develop this one before I come here, because my Mac does not have the Ansys Fluent, so I cannot show it here. That's why I told him. He did it very slow and very nice way. He showed all the possible areas that you can do it. I think you just follow that, and if you want to do practice after that, you can just replay, and then you can. I think at first you don't need to start by yourself. Just listen. It's about 40 to 42 minutes. Okay. See how it is. It's mostly everything the same. Only the problem is to how you want to introduce the particles. Okay. There are some tricks. So that tricks, if you know those tricks, because you already know how to model the airflow. Only extra thing is like how to use the DPM model. Just add those particles, distribute those particles, give the particles properties. That's it. It's not very tough. So I'm just playing the video, and if you have any issue anywhere, just let me know. I can explain. I can pause the video and I can explain to you. Otherwise, just listen to it. And it's my Chinese student, so he tried to slow, English very slow, but English is good. You will understand. But if you don't understand anywhere, just ask me. Okay, I'll explain to you.
File location, and we'll start by opening the workbench and find the fluent component. And because we already have the mesh here, .msh file or other formats.
So here what happened is we already have the mesh file. So we are not showing here the geometry creation and meshing it. So we will be using directly the mesh file. Okay? You already have the mesh file and you know how to do the meshing.
Sir, is there any way to get these sort of geometries from some repository or something?
But here we use a long pipe. Only a pipe. Yeah. That's why for the demonstration purpose. But this geometry is no. This geometry is, that's why I said this geometry is not available. Okay? Because once you have this geometry, is not very tough to do the modeling. So that's why nobody wants to give this one. Okay? And that's why if you want to collaborate with someone, then maybe they can share the geometry with you, because it takes long time to create the geometry. So that's why they don't want to give to anybody else.
This geometry is created that
Which one, sorry?
your geometry.
Yeah.
It is created in this software.
A couple of softwares. So I can show you some. Just a sec. I can show you. Where is my mouse? Oh, mouse is here. I can show you the OneDrive. So this is the proof of this book chapter I said. So this is the techniques of aero structure modeling. So here we give very details Okay. So this is the student who is actually explaining here. So this is my student, he is explaining here. And this is my student, she came here for 1 month in IIT Kharagpur to do some experiment. Okay. So in this study, you can see, so start from the very simple geometry, okay, and then a lot of things. He actually reviewed all this study, all by doing by himself, and then this is the details. Which software is used, okay? Everything is very like image segmentation. So in details, it is written here. What kind of software they use, okay? So mimics medical. So this is the one software. They use mimic medicals, and then also a lot of other softwares is there. For meshing, they use other software. So GeoMagic, they also use a GeoMagic, okay? GeoMagic wrap. Yeah, couple of 3 or 4 softwares actually you use to do this. And step by step, everything is written in this one. So once this book is published, so it will be available. So if you are interested, or if you can send me an email, I can share this chapter to you, okay? All right, so that's what I said. So only we start from the meshing. We have the mesh file. We use point-wise, I remember. We use point-wise software for meshing. So point-wise software is very easy. Easy means you have control how you are applying the mesh. It's not like the Ansys meshing. So in that way, we just use the point-wise, and we generated the mesh, and now we'll import in here. Okay. No, this geometry is very simple, like a pipe. Otherwise, we can't show it here like a simulation. Yeah.
I'm asking like once the geometry is created, you have used 3 or 4 maybe softwares to create a geometry, but mesh is done here.
Yeah, we just created geometry, all those softwares, and then use the point-wise to create the mesh, and then import in the Ansys.
So meshing is done.
You can do the meshing outside. Yeah, not a problem. Okay, meshing you can do outside.
For meshing also you have used Ansys software or
No, it is not mandatory. So you can do meshing outside and bring it here. And not only that, actually you don't need this like this system. You can directly go to the Fluent. Okay, there are all the components. Okay.
asking like is that the meshing is created this software using this software?
No, not here. In point-wise. Point-wise is another software. So we use this point-wise software for mesh generation, and then we save the mesh as .msh, and then just we read it here. Okay.
That is compatible. We can go directly to setup instead of mesh or geometry. However, if you wish to create the mesh from scratch, we'll have to start from geometry. But in this case, since we already got it, we will start from setup and double click it, and you have this panel. We can do the double precision so that we can reduce the numerical error. We can here customize how many computer cores or parallel computation that we utilize during the simulation. And here we can set up, for example, 16. Start. And now we are in the panel. Let me see. First go to File. and import mesh. So go to the file location. And as you can see, here the software didn't notice our file's existence because I guess our mesh file is from the older version. Now they're using .mesh, .h file. However, our file is not is only .mesh, not without the h file compression format. So we'll just click on all mesh files, and then you can see this file. Or in other cases, you can choose all files. Same. So select it and click OK. And now the computer is loading and doing parallel sectioning of the mesh. Here at the console panel, you can see all the information. We'll just wait for the computer to... I think it's already done. Okay, now here if the mesh doesn't show, you can click on display to show the thing that you wish to present, or that is easy for you to conduct simulation. There are a variety of ways to display your mesh. Here, for example, perhaps we can choose edges and features and display. And here is a simple outline of our tube geometry, or it could be a section of the airway. The dimension is set up according to roughly secondary bronchi dimensions. Okay. And we can close this panel. And now we can set up the simulation. Here it can be a steady. If you go to the general panel, here you can see that it could be a steady or transient simulation. Here we can enable the transient simulation. If we want to employ a dynamic changing breathing profile, we'll have to go with the transient simulation. Here we can enable the gravitation. Check the model. Here you can see a coordinate lined up. So now we can see that the y-axis it goes like this, vertical. Into the tube geometry, we can set up this axis as the gravitational axis. However, you can set up in different direction using the 3 components. Okay. So notice the unit is meters per second squared. Okay. Next, one thing we should also look at is the scale to check that this dimension of your mesh is reasonable. Sometimes when you import meshes from different softwares, the dimension might be wrong. Maybe x max is 2 meter and negative is 2 meter, it'll be a 4 meter in x dimension, and that will be totally inaccurate. And here you can use scale to change the dimensions. You can scale it down or larger. And now let's go to the models. Here you have a variety of computational model you can enable. For example, here, if we consider energy, we'll have to double click it and click on the energy equation to enable it. But here we don't need it. We'll just go to the viscosity model and choose SST K omega. There's two equation model, and this is a very robust model that can handle a reversed gradient pressure gradient for that typically exists in lung geometry simulation. And these profiles are all by default, and be sure to choose SST. It's one of the most advanced K omega model compared to the previous ones. And click on OK. So now you have the viscosity model set up. And next, we could choose the discrete phase. Open the panel.
Can you say again?
Will there be turbulence in this case?
Double the speed?
Turbulence.
Yeah, they use turbulence, sorry. Yeah, they use turbulence. Because, I don't know, this student, is he should not use the turbulence, but because he is using turbulence for the whole lung geometry, he used the same model here.
No, so in the whole lung there is turbulence.
There is turbulence, that's I said. Even though for small airways, like as I said, the small Reynolds number, 100 Reynolds number, you can experience some turbulence here near the larynx. Okay, that's the reason they just use the turbulent model. So you can see most of my papers published is all turbulent model.
So there is one thing, low turbulence correction given in there. So should we use that? Because major of the flow is laminar. Only at a certain point it is getting turbulent.
Yeah, that's true.
Should we use that?
Yeah, that you use. Yeah, that's your that different way we can do it. But I don't know how to do it in the Ansys this one. So that's why I use. Yeah. So but in industry, that's why you can see that the default one is K omega model. Industry, they use K omega model in every case, even the laminar. They don't care about that because that is faster. Because they use model. Use model means they are not solving the whole equations. They are actually modeling it, making it simplified. But for research, we should not use it. So because he is very used to use it for the whole lung, so that's why he used this one. But you can use laminar for your case. Okay.
And here you can have a lot, you also have a lot of information here, such as unsteady particle tracking or interaction with continuous phase. I won't go into detail there, but here I recommend to just type in
These are tricks.
like 3 more zeros here, make it larger. And physical models. Now, if we want to simulate a particle inhalation, like if we enable supplement lift force, we consider the rotation effect of the particles. If the pressure gradient is also a thing, and there's many things we can choose, such as stochastic collision to model the random collision between particles. but here we'll just go with the self-manly first for today. UDF are user-defined function that you can employ to model the DPM phase in whatever way you like. And these are all by default. You don't have to change anything. So just click on OK. And now we can add in injections. Here, you can create injections. You can create multiple injections actually from here. Sorry about my computer is lagging. So we can name it as injection 0. And the reference frame is here. And the injection type is single or group. Single is it sounds like it releases the particle from a single point. Here from surface, however, it releases particles from a certain surface at the grid point or mesh point. However, it releases a group.
Yeah, so I am to just emphasize here. So you see, this is a very crucial area. How you want to distribute the particles in the inlet. So that is very important. Okay, because when we started in 2012, there was not much way. So now they increase a lot of way to distribute particles. So that time we had only the single. As a source, you can release the particle from the source. It is not realistic. Okay, so now they have a lot of things you can release as a group. Okay, or you can use a surface. Surface is the very important one. Surface means you can distribute whole surface in your nose or your mouth. Okay, inlet you can just give that way distribution, or you can use as a volume, or you can use as a cone. Okay, big to small, so particle is coming through that one. So yeah, now lot of things you can use. Mostly we can use the surface, and not only the surface is generally they use the note points. So note point means maybe on the inlet surface you have 200 nodes. So that means they can only release 200 particles. But if you want to do more, you can actually do that. So there are some other technique. So here actually he will explain all these things. So we use the surface one. Surface one is the most popular. But you can actually go through each one of them and you can test.
Sorry, what is taken in case of volume? Because the next one is cone should also be a volume. How do you separate like for different volumes?
Yeah, I think you should go through each of these. So we did not go very in depth some other cases because we just use for the surface, and we found in that area many people they use only the surface. So I think it is not for the lung, but for some other application they use this one. Okay, there are some particles maybe generated somewhere in some system, so they maybe use that one. So for the lung purpose, the surface distribution is the important.
Single is it sounds like it releases the particle from a single point. Here from surface, however, it releases particles from a certain surface at the grid point or mesh point on the surface. For example, if we choose in surface, maybe we'll have a look at the difference between different geometry names. So we'll have like in and in 0.07. Let's say what they are phases. So as you can see, the in is a tiny surface created during the boundary layer creation. It's a thing that typically exists if you use ANSA meshing software. However, if you use other meshing software, they will merge the surface in and in 007. You can see 007 is the internal surface. If you enable 2, you can see that the two surfaces combined together forms the entire inlet. And now we can decide the injection and location. We'll use the we'll choose the surface release, and in 007 here we will release particle from this green surface and not from this boundary layer surface. However, in your simulation, you can choose based on your condition. And here are the particle type, and just go with inert material. We can simulate, for example, a water liquid aerosols. So they're the material is water liquid. Diameter distribution, for example, you want to release particles not of one diameter, say that 1 micrometer, you want to release 1 to 10 micrometer. However, how do you release 1 to 10 range of micrometers particles? You have to tell the computer that you release it like 1, 2, 3, 4 micrometers, or 1.5 to 2.5 micrometer. Here is the distribution equations that tells the computer how to distribute a range of diameters of particles. Uniform one is the simplest. It's just 1 diameters. We can choose a Rosen Ramler. Let's go with that one. So here are the point properties menus. You can choose variables velocity, the velocity of particles that enter the release from the surface. So in this time, we'll just go with 0 velocity. So the particle are released on this surface as 0 velocity, and I assume the inflow of air will carry forward. And this might not be realistic, and might not be what is really happening in our lung, but here is only just a tutorial for you to get use of Ansys Fluent. So start time is the time that I wish to release the particles. Because we're doing a transient simulation, we have start time and stop times. If it's a steady state simulation, this option will not exist. So for transient simulation, we want it that we kind of want the flow field to converge, the continuum phase to converge. We might want it to run a few steps, maybe, run a few steps. After convergence, then we release the particle. It's better for calculation stability. However, when you input these numbers, you should always consider the need of your simulation. The stop time can be 0.5. So we'll release a particle from 0.1 to 0.5 seconds. What else? For the surface injection type, we can also with let's see, perhaps group. Actually, let's just go with surface. Okay. So the total flow rate by default is 1 to the times 10 to the power of -20. Here is also a thing that you need to consider during your simulation. So because we're releasing very few amount of particles, aerosols, we'll just use the minimum one, like barely, almost ignore the existence of these particles in the continuum phase. So here are the minimum and maximum diameters. The minimum is 1 times 10 to the power of -6 meters. That's 1 micrometer. And here is the maximum diameter is 1 to the power of 10 times 10 to the power of -3. That's 1. Micrometer. If we do it this way, and this is this 1 to the power of -6 to the power of -4, and this to the power of -5. If we do this way, then we are releasing particles from range from this to this range, and that's if we use the mean diameter as 1, how about?
So here a couple of things you need to consider. So one is your start time. Okay. So what he mentioned is, because if you introduce particles and also the air together, so there may be some problem with the convergence. So it's better you just run for a couple of time steps, get your solution converged, and then you can introduce the particles. Okay. So that's why he start with the 0.1 second. So in 0.1 second, he release the particles. And this is the total flow rate, because we use very small number of particles for this simulation. That's why we use very small rate of flow. The flow rate is very small. And then how long you want to release the particles. Okay. So you can calculate. If it's like a breathing pattern, okay, like inhalation and exhalation, you can also set up. Okay. How long you want to set. You can do everything here. Like you can write some UDF as well. So that's why he just make that those particles will be released from 0.1 second to 0.5 seconds. This is the time you are releasing the particles. After that, only you are inhaling air, nothing else. So now about the particle distribution. So what will be your the diameter, the minimum diameter and the maximum diameter. Okay. So minimum diameter, he use 1 micron size particles. Okay. And the maximum is 10 to the power -4, means 100, right? Yeah, 100 micron. So 1 to 100 micron particles, this one. And now, because we are using the Rosen-Rambler distribution, so you can see everywhere is help. So click the help, and then it will open up all the details of these things. So what is this diameter distribution means and how it works? So everything is very, very details. I think you should sometime go to see it, what it is. So now here he is giving like the mean of these two. That means a mean distribution. Okay, this, or you can give like you need more particles close to 100 micron. So you can give like a 80 or 70. So then the distribution will be like that. Okay, this is the way we just distributed.
How do we know about that air? Because in the material it is only given water liquid.
Yeah.
So how do we know that air is also there?
Oh, here model already there. Is already we set it up. Okay, and this is you see the model at the left side, a viscous SST. No, on the left side. Multiphase energy and viscous SST. So that actually for the air flow. And here is just discrete phase, that is the particle flows. So they are actually combining these two equations.
Five times 10 to the negative 5, and it's like this is 1, this is 100, and this is 50 as the mean diameter. 1 micrometer, and this 100 micrometer is 50 micrometers, and here, yeah, in this way we'll releasing 100 particles, like from 1, 2, 3 to 100 micrometers, not 1, 1.5, 2, 2.5. It's just 1, 2, 3. Yeah, I think so. The spread parameter is the parameters that you use to control the distribution pattern of the Rosen remnant. I won't go into detail about that. Let's see. Number of diameters will do is 100, so that is 1, 2, 3, all the way to 100 micrometers. And click on OK. And there you have it, an injection 0. And you can always change the parameters here with this setting. And now to the material, it's already set up because you chose water liquid during the discrete phase here. In the inner particle already showed up, and the air material, in case it doesn't show in your place, you can click on anything. For example, the water liquid you just set up, and go to the fluid database and find fluid, solid, or inner particle. You can find fluid, and just go down. You have water, liquid as fluid, but we wish to have air here, and you can just copy. And because we already have it, it'll create a new one, air new, so we just cancel it. Okay. Now you have air and particle material. So the material panel is set up. And now to the cell zone condition, the fluid. So here initialize the volume of our tube. We can change or check what is set up here. So it's air, so it's okay. If it is not, you just choose air. And it's the same here because because we're using a different machine software, and this software, when we create the boundary layer, it also creates like 2 surfaces and 2 volumes. One volume for that connect to this surface is the boundary layer volume, and here is just internal volume. So here you can see 2. You can also check here. It's air. So we apply, close. And now so now all the volumes are fluid and are initialized as air, and that's great. If you have other cell zones, you can also set up in the same way. Now to the boundary condition. So So here, it classified everything as wall, and that's incorrect. So we'll just change it in as the velocity inlet. Let's see. Yep. And go to wall again, out as pressure outlet. Yeah, pressure outlet. And now the wall is only wall. We can check the wall setup here. So if you have DPM, we can, in the momentum panel, you don't have to set up anything. But for the DPM, you have to trap. So that once the particle attach the wall, it will be tracked by the wall, and the simulation stop calculating that particle's trajectory because it's already trapped, and it'll disappear from the simulation. And later on, we can collect data at all the trapped particles' position and time. Okay, so we finished set up the wall, and now let's set up the velocity inlet. Here we can do multi-edit so that we edit the two together, boundary together. So the velocity magnitude we can set up as, I don't know, let's try with 1 meters per second. That's a relatively high number. I assume when we breathe in our nostril inlet, the velocity can reach 5 meters per second. So we'll just go with 1. It's a reasonable number. However, during your simulation, it has to be carefully considered. And just apply. And let's set up the outs. We can also display it. Doesn't show. Yep, here, display everything. You can see that this is in, the arrow pointing inwards, and out, red arrow pointing outwards. Click on the middle of your mouse and you can rotate this object. So let's set up the pressure outlet. It could be pressure outlet or user-defined or velocity outlet, depending on your simulation required. Here we set up a 0 gauge pressure outlet. Is not realistic, but it's just for the time being, we'll just use 0. And the particles, I forgot to set up the particle of the inlet. So our particle should be escape, because when the particle reaches the outlet, it should escape. Apply. And so here you can also see here, and the two boundary condition changed to discrete phase boundary type changed to escape. Here, let's set up the inlet DPM. It should be. So here we inject the particle from the inlet. So we shouldn't choose track because we just injected it. Oh, we don't want it to be tracked. It should not be reflected. Re-inject is one option. That if the particle we just injected it, if it escaped, it went from different to a different direction. It escaped the computational domain. We just re-injected it again. So using the injection, or simply you can just choose escape. Just let it escape, because in our simulation setup is a simple case. It'll definitely not escape. You can just choose this as a default, as a safe one. And the internal surface boundary condition, you don't have to set up anything. It's just, yeah, there's nothing to set up. So now I think we finished the boundary condition setup. What else? Now go to the solution. We can choose the method. Here is a simple method. It's the most simple one, and you use it. It might not achieve the best calculation precision. It might not be stable for complex geometry and complex modeling, but it's the fastest. Everything is default. You can, however, you can change it to to other options. So this menu, if you the first one is it usually is less computational resource required. The final one is most computational resource intensive method. If you all go with the final one, it'll take a long time for you to finish the simulation. However, it might achieve a better numerical precision depending on your topic and your case. The control on the relaxation factors, I will not go into detail about these. So just go with default. Report definition, here you can set up different parameters. For example, you can create new ones. Here, surface report, you can extract data such as area weighted average of wall pressure, or or static pressure, and you can name it as this one by default, and click on OK, and then you have it. You have one more extra report definition of area weighted average pressure, static pressure of our wall. And later on, you can plot graph or just export the data of the area weighted average static pressure of our wall. Monitors are residual monitors. You can just choose it. This is how we control the residual. If you make it very small, the simulation the software will calculate the residual to these values to consider it step converged, iteration converged actually. So we will not go with that far. However, if you're using a double position solver, as we set up earlier, we can go with a smaller value. Okay, just click on OK. Everything is default by default. And report file, we just define a new definition, and here we can see a report file. Here you can plot delta time and time step, or not importantly, just choose these two, the area weighted average static pressure of the wall and the flow time, and these two numbers will be printed out in a file as an .out file with the location that you choose. For example, we'll just go with default one and get data every time step or flow time. For example, I want data every 0.1 flow time. you can choose differently or every time step. So if you have 10,000 time step, you have 10,000 pair of data here. Every time step calculations of every weighted average of static pressure for lung will be printed there in this out file. So click on OK, or you just delete it. If you don't want the file here, you can delete it. And report plot is just the definition that we just created here. The plot you have, you already selected. Yeah, so that after the simulation, it can plot the line graph or a dot graph of this parameter. Let's see. Now let's start the initialization. We'll do with the hybrid initialization. It's usually better. It helps you to stabilize the simulation initially. So just do the initialization here at the console page. You can see that it's already initialized and the value is very small. That's a good sign. Calculation activities, you can enable the autosave to save the files every time steps. So if you like, for example, if your computer run off battery and the computer shut down, but you saved every time step. Here I don't want to enable it this time. However, for your daily exercise or experiments, it's highly recommended to enable the autosave. You can customize the saved data. Actually, you can output these data. There's 107 data you can select to save. Here we already select 36 of them, but you can add more. Click on OK, for example. But here we don't want to enable it, so just cancel it. And now we can run the simulation. After initialization, actually, here we already enabled the results graph. For example, particle tracks. We can track our injected particles based on and colored by resident time or particle ID. Just choose whatever. Point or sphere. And save and display. Because we haven't released any particle during our initialization, so this should be blank. And now go to the reports and discrete phase and go to sample. And here is one of the most important part. We collect the particle that deposited on the wall. So we just click on wall and injection 0, and we can append file and start. So once we click on start and then start the calculation, this file, the machine will create new files and store all the particle information on the wall to this file. Maybe we'll just go with out. We also want to see the particle escaped that passed through these two this outlet surface. So start. So now you'll see warning from console, it says unable to append file because you don't have an existing file to append, so it's creating new file, and you'll see a lot of repeated warning. This is because you use parallel computing. We set up 16 at the beginning, so you'll see 16 repeated warnings. The particle data also parallelized into 16 to calculate it by 16 different cores. So we don't click on stop until we finish the simulation. And now run the calculation. Here is the number of time steps you want to employ or use adaptive. Here you can set up the total time that you want to simulate. For example, 10 seconds. And set up here, you can set up the minimum time step as 1 to the power of negative, say 3 should be enough. You have to do some research about that. And yeah, if you set up this way, we can increase the maximum iteration per time step to allow that the simulation converges on every step. However, if your simulation takes 200 steps to converge every iteration, it means that your simulation is not that good. It's not converging. It's very unstable. Ideally, your simulation converges 20 time step every iteration. But here it's just for the sake. Yeah. So now, initial time step size. Let's check. Well, so here is initial time step size. We'll start the simulation with this time step, and we can set up the minimum and maximum time steps and factor. Here is an adaptive time stepping. We can, if the time step is too low, it's too small, we can increase the time step so that we can finish the simulation faster. And the standard to increase or decrease the time step is given here. Then it's given where? Is given here. The current number we set up as 1. Yeah. So you can set up differently. But here we use 0.01, and also the minimum time step is 0.01. So if according to my experience, the entire simulation will use the same time steps as 0.01 seconds. Okay, let's calculate. Yeah, the computer is taking a very long time to calculate. Let's wait for a few seconds to see if it starts. So here is still saving the file to your location.
He's not very professional. He's not very professional. So I think this is the first time he made video for me. So that's the reason. I think he should stop the video recording now and he should wait until the simulation is finished and then he could show the analysis. But anyway, it was taking time, that's why he stopped. He did not do the simulation and did not show it. But still it's very good. It shows details and it will be saved in your video. So you can rewind and then you can set it up. But still we have some time in our hand. How much? We have about, we have about 40 minutes in our hand. So if you want to practice, because you already have the file, the pipe, okay, either the bifurcation one or the single pipe yesterday or day before yesterday you used. I think you should now do a little bit of practice and add the particle information, because you have other information already have done for the airflow, okay, and then just add those particle information and you can run and you can do some testing, okay. So you should do some practice before Professor Chakraborty comes and we organize the final session, okay.